This is the moment you've been waiting for. And a few of you have asked, what do we do with this stuff? Why do we find derivatives and set them equal to 0? Well, the answer is to solve problems. Just like algebra was invented to solve problems, calculus was invented to solve problems. And a specific type of problem that we can solve with calculus is answering the question, as this changes this fast, how fast is this thing changing? For example, when you're blowing up a balloon, as the volume of the balloon expands at a certain rate, and I'll tell you what that rate is, how fast is the radius changing? Or as a horizontal distance changes at a certain rate, and I'll give you what that rate is, how fast is the vertical distance changing? All of these problems are asking something to the effect of how fast is one thing changing if I tell you how fast another thing is changing. Tell me what, when you see dy over dx, which is not what I wrote, dy over dx, how do you read that symbol? The derivative of y with respect to x. Now, we don't always say those words when we're just labeled the derivative y prime, but so far, whenever we've differentiated, we've been differentiating with respect to x. Well, x is not the only thing we can differentiate with respect to. Today, we're going to have derivative of y with respect to t, and that t is for time. That's a change in y as t is changing. So when we have quantities that depend on time, we can differentiate those quantities with respect to time. For example, it's page 182 in the 5th edition. It's somewhere close to that in the 6th edition. If we were draining water out of a conical tank, then both the height of the water and the radius of the water at any given time would depend on the volume of the water. When the volume of the water is right here, the height is bigger and the radius is bigger than when the volume of the water gets down to here. The lower the volume of water, or the lower the water level, the smaller the radius and the smaller the height. So we can differentiate all of those variables with respect to time. Radius is a function of time, height is a function of time, volume is a function of time, and we will use symbols to indicate that when we're differentiating. When we take the derivative of the volume with respect to time, we're just going to use the symbol dV over dt. And we're going to start calling that the derivative of volume with respect to time. On the right-hand side, take the derivative of this with respect to time. What would it take to differentiate that? It's a product. You would take the product rule. So I can just keep up with the 1/3 or the pi over 3 and say the derivative of r squared h with respect to time is the first factor, r squared, times the derivative of height with respect to time, plus the second factor, h, times the derivative of r squared with respect to time. The derivative of r squared with respect to time would be 2r dr over dt. So we're using the chain rule. We're saying volume is a function of time. I don't know exactly what that change is, so whenever I differentiate v with respect to t, I'm going to be sure to have a dv over dt in my answer. Radius is a not factor, what's the word I was just using? What? Yes, function. How does a math teacher forget the word function for a minute? Like that dog slipping off into the water. Radius is a function of time, so whenever I differentiate r, I'm going to have a dr over dt. Height is a function of time, so whenever I differentiate a term with an h in it, I'm going to have a dh over dt. now I have a formula with 3 rates in it, dV over dt. They could have just brought that straight down. dV over dt is the rate of change in volume with respect to time. dH over dt is the change in height with respect to time, and dr over dt is the change in radius with respect to time. You give me a particular radius, a particular height, and then 2 of those rates, and I can find the 3rd rate. The most important thing to realize in this section is when you have quantities that are functions of time, when you take the derivative, you're going to have d, whatever that quantity is, with respect to time as part of the derivative. All right. There's one thing I want to show you on the next page, and then we'll work some examples. I'm either going to give you an equation, or I'm going to give you a problem that uses some equation that you already know, some geometric formula or some trigonometric formula. Anyway, you're going to start with an equation. I'm going to give you one rate at some particular time, and then I'm going to ask you for some other rate. So if I give you the equation y equals x squared plus 3, you can differentiate both sides with respect to time. The left-hand side will become dy over dt. The right-hand side will become 2x dx over dt. If you substitute in dx over dt is 2 and x is 1, then you can find that rate of change that you're looking for. So you start with an equation. I give you all of the values of the variables except for 1. You solve for that one equation or that one variable. Example 2 is a pretty good example. So we'll talk about it, and then we'll start doing some from the exercises. A pebble is dropped into a calm pond, causing ripples in the forms of concentric circles, which we've all seen before. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, what is the total area of the disturbed water changing? At what rate is the total area of the disturbed water changing? Just say like you can't see anything below that for just a second. What geometric equation does it sound like we would use to work in that problem? We're talking about area of a circle. And we know a formula for area of a circle. That's the equation we're given. Now, if on the test, if I give you something I know you've been working with since the 8th grade, like area of a circle, or circumference of a circle, or perimeter of a rectangle, I'm not going to provide those formulas to you. But if I give you something that I know you probably haven't been working with every day since the 7th grade, like volume of a right circular cylinder, I will give you that. All right? You don't have to memorize every geometry formula there is. I will give you that. For the homework, I think all the formulas you need are on one of the covers of the book. Inside front cover or inside back cover gives you all those geometry formulas. But I would expect you to know A equals pi r squared. All right, the rate that we're given is how fast the radius is changing. We're given dr over dt. That's the symbol we'll use for the rate of change in the radius. dr over dt is 1 foot per second. What we're looking for is the change in area. What symbol will we use for the rate of change in area? dA over dt is what we're looking for when the radius is 4 centimeters. So we're going to take that equation and differentiate both sides with respect to t. The left-hand side will be dA over dt, and the right-hand side will be 2 pi r dr over dt. And of that differentiated equation, there are 1, 2 rates, and 1 other variable. So really 3 variables in all. You give me the value of 2 variables, I can find the missing one. The two things that you gave me were dA over dt. No, you gave me dr over dt is 1. So put 1 in place of dr over dt. And you said when the radius is 4, put 4 in the place of r. That area is changing at 8 pi. What would the units on that be? It's a change in area. What do you know about quantities related to area? They all have something squared. Our radius is measured in feet, so how is our area going to be measured? Square feet, and since it's a rate, it's not just 8 pi square feet, it's 8 pi square feet per whatever the units on our time were. This is 1 foot per second, so this is 8 pi square feet per second. All right. Of course, they're going to get uglier, but we do the very simple one to make sure that you understand the process. And once you understand the process, the hardest part in some cases is going to be coming up with that equation. Not today. Today, by the way, we have 3 days to spend on this section, so we can really go slowly and make sure you understand it. But the problems that you're given today, you're given the equation, and really I don't think of them, any of them are any more difficult than this one. All right. Page 186. By the way, there's no real, there haven't been any notes in momentum for the last couple of sections. I can't really give you notes on word problems. We just do word problems. But once we get to chapter 4, you'll need to start printing your notes again. All right, page 186. Number 4 gives us x squared plus y squared equals 25. Assume that x and y are both differentiable functions of t and find the required values of dy over dt and dx over dt. If we were to graph this equation, what would it look like? It's a circle. So let's play like we have a marble rolling around the perimeter of a circle that has centered at the origin and has radius what? Okay. So we have a marble. Don't laugh at my circle. It's not my worst circle day. We have a marble rolling around the perimeter of that circle. I don't know if it's rolling clockwise or counterclockwise. If we say it's going in the positive direction and trig, that means counterclockwise. It's moving through the first quadrant first and then moving through the second, third, and fourth quadrants. If this marble starts at the point 50 and is going counterclockwise, it's going uphill, right? What's happening to the x values as that marble rolls uphill? They're getting smaller, and what's happening to the y values? They're getting bigger. And the circle reaches, or the marble reaches the top of the circle at 0, 5, and keeps rolling. As it keeps rolling, what happens to the x's? When they're getting closer and closer to negative 5, they're increasing in a negative direction, and your y's are getting smaller and smaller, closer and closer to 0. So I can see that x and y would both depend on how long the marble's been rolling. All right, x is its horizontal distance from the origin, y is its vertical distance from the origin. Both x and y would depend on how long the marble's been rolling. So I can differentiate both of those variables with respect to time. All right, what would the derivative of the first term be with respect to time? 2 what? Derivative of x squared. 2x derivative of x with respect to time. X is some function of time. I can't express it explicitly. So whenever I differentiate a term with an x in it, I'm going to have a dx over dt in it. All right, what about the second term, the derivative of y squared with respect to time? 2y times dy over dt. And the derivative of the right-hand side is 0. We've differentiated both of those sides of that equation with respect to time. Now let's see what we're asked for. In the A part, we're asked for find dy over dt when x is 3, y is 4, and dx over dt is 8. 3, 4 is a point on that circle. And we're given the rate at which x is changing. We're asked to find the rate at which y is changing. Well, had you rather solve for dy over dt and then plug numbers in? Or would you rather plug numbers in and then solve for dy over dt? Most of us prefer to work with numbers instead of letters. So I'm going to plug these values into that equation and solve for dy over dt. 2 times x, which is 3, times dx over dt, which is 8, plus 2 times 4, y, which is 4, times the thing we're looking for, dy over dt, equals 0. That's 6 times 8 is 48, plus 8 dy over dt is 0. 8 dy over dt is negative 48. So dy over dt is negative 6. Now, we're not necessarily going to write a whole sentence at the end of every problem, although that's really a good thing to do in word problems. Make sure you understand what it is that we have found. I definitely want to write the sentence here, though. If we are imagining a marble rolling around that circle, then when the marble is at the point 3, 4, and the horizontal distance, instead of distance, let me say horizontal component is changing at a rate of 8. We're not given any units here. So the best I can do is units. I don't want to just write units per unit. If we play like, yeah, if this problem actually was a word problem instead of just practice the algebra problem, let's say it said x and y are in inches and t is in seconds. Let's say that that had been part of the original problem. Then what would be the rate of change, or what would be the units on this rate of change in horizontal component? Yeah, it's not just inches, it's a rate, so it's inches per something. Inches per second. When the horizontal component's changing at a rate of 8 inches per second, the vertical component is changing at a rate of -6 inches per second.
Now, when you take just -6, you would need to write that.
You don't have to write me, although I think if I were a better teacher, I would make you write me a complete sentence. I do want you to at least give me units. I want to know if that -6 is dollars, inches per second, or ducks. That matters, ducks. So give me at least some units there. But I wanted you to understand what that problem was saying in terms of everything that you were given. All right, I think I'm not even going to do the B part. The B part's the exact same thing, but they give you a dy over dt, and you have to find dx over dt instead of the A part where they give you dx over dt and ask you to find dy over dt. It's the same. So let's move on to something cooler. Number 6. The paragraph right above number 5 through 8 say a point is moving along the graph of the given function at the rate dx over dt. Find dy over dt for the given values of x. So again, we're having a marble that's moving around the curve. And you could even graph it on your calculator to see what curve the marble is moving around. I've already done that just to save us a little bit of time. That's the graph of 1 over 1 plus x squared. So we have a marble that's rolling uphill for a while. It reaches a peak right there at when x is 0, y would be 1, and then it starts tapering off again. And what we're given in number 6 is that dx over dt is 6 inches per second. That's the horizontal progress that the marble is making. The marble is moving horizontally at 6 inches per second. We want to find dy over dt, and then we have 3 parts of the problem when x equals -2 is the A part. A common mistake in these problems is to start plugging in numbers too early. Right now, if I put -2 in place of x, what would y equal? 1/5, and what's the derivative of 1/5? 0. That would be an easy problem. But x equals -2 is not a constant value in this equation. It's just one particular value. I could give you x as anything. I want to differentiate that equation and then substitute in the given values. So what's the derivative of 1 over 1 plus x squared? You want to rewrite it so that you don't have to use the quotient rule, or do you just want to use the quotient rule? I say just use the quotient rule. You don't have to. Do it your way, and let's see if we come up with the same thing. When you take the derivative of the left-hand side, you can't just use the symbol y prime because that doesn't show what you're differentiating with respect to. You have to use what instead? dy over dt equals the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. What have I left out? When I take the derivative of the term with an x in it with respect to time, actually I can just put it out here as long as I include it, that's fine. All right, let's clean that up just a little bit. And now that I've differentiated, I can find any rate of change in y for any x that you give me, as long as you give me the rate of change in x as well. And that was given to me in the A part when x is -2. And dx over dt is 6. That's what dy over dt would be. What are the units on that 24/25? Inches per second. If that were a change in area, I'd have square inches per second. If it was a change in volume, I'd have cubic inches per second. But since it's just a change in linear distance, then it's just inches per second. What that means is if this marble is rolling up this graph and gets to the point where x equals -2, let's say x is -2 right there. So the marble started rolling here, it's made its way up to there. dx over dt means the marble is moving, or dx over dt is 6, means the marble is moving in what direction? To the right. That's dx over dt is a change in horizontal distance with respect to a change in time. And so a positive change in horizontal distance means the marble's moving to the right. As the marble's moving to the right is starting at -2, is it moving uphill or downhill? It's moving uphill, and that's why we got a positive change in y. If we skip to the, well, actually I don't want to skip. I want to do the B and the C parts. The B part says when x equals 0, I don't have to do the differentiating again. I have dy over dt is -2x over 1 plus x squared times dx over dt. Now I'm just putting 0 in place of the x and 6 in place of the dx over dt. What's that? That's 0. What does that mean in terms of this marble rolling along that graph? It's a, ooh, that's another good word. 2 good things I heard right there. One thing I heard was it's at the top of the graph because when x is 0, that's on the y-axis, and that's the high point of that graph. Another good thing I heard was that's the maximum value. That's where the marble reaches the highest point. So when the marble reaches x equals 0, it stalls out for a split second, and then it starts rolling downhill. All right, then I'll answer, let me say one other thing, and then I'll see what you need. The C part, I do want to move on, but if we found dy over dt at x equals +2, would you expect to get a positive or a negative value for dy over dt? Because at that point, the marble would be rolling downhill. All right, Glenn, what was your question?
So is this kind of the same as finding the slope of the tangent line?
Absolutely. Absolutely. That's exactly what it is. All right. That took a little bit longer than I wanted, but that's okay. We got 3 days. Let's, I think I might only have time for 2 more. So I'm gonna skip number 8. I was gonna do it, but let me just say, I know you can do it. This is a marble rolling around the graph of cosine x. You know what cosine x looks like? A marble rolling along cosine x at its horizontal rate of 4 centimeters per second. You just want to find the change in vertical rate or vertical distance with respect to time at each of those 3 values. So find dy over dt and then plug in those 3 values. To get where I want to get, I need to skip to number 14. I would like to get both 14 and 16 done. We'll see. Number 14 says a spherical balloon is inflated with gas at the rate of 800 cubic centimeters per minute. How fast is the radius of the balloon changing at the instant the rate is, and then there's A and a B part. What formula do I need to look up inside the front cover or back cover of my book? Go ahead and look inside the front cover of your book and see if you can. I need volume of a sphere. You probably haven't been using that one since the 3rd grade, so I'd give it to you. It's 4/3 pi r cubed. All right, that's the equation that I know I'm going to have to use. Now, what are we given? The spherical balloon is inflated with gas at a rate of 80 cubic centimeters per minute. 800, I'm sorry, 800. What is that 800? Your clue is that 800, the units on that 800 are cubic. Anytime your units are cubed, that's volume. So that's not volume equals 800, but the rate of change in volume with respect to time. You said it exactly right, Major. That's dV over dt is 800. And I'm just going to put cubic centimeters per minute so that I can remember what my units are. All right. Then it says, how fast is the radius of the balloon increasing? Change that to a sentence that begins find. What are we trying to find? All right. We're not trying to find a radius. We're trying to find a rate of change in radius. So, sounds right. We're looking for dr over dt. And I have to be given one other tiny bit of information, and it's the information in the A and the B part. We'll just do the A part. The A part says when the radius is 30 centimeters. The B part, the radius would be 60 centimeters. All right. What's the derivative of the volume of a sphere formula with respect to time? Left-hand side would be
V or dV over dt.
derivative of volume with respect to time equals what?
4 pi r squared.
Hey, is this going to take the product rule?
I don't know.
No, because 4/3 pi is a constant. You're just going to multiply the exponent times the constant. That's 4 pi. Subtract 1 from the exponent, and don't forget what? The radius is a function of time, so you have to have a dr over dt. We're looking for dV, no, we're looking for dr over dt. Had you rather put numbers in and then solve for dr over dt, or solve for dr over dt twice? Yeah, I'd rather put in the numbers first. So 800 in the place of dV over dt. 30 in the place of R. And we're solving for dr over dt. dr over dt would be 800 over 4 pi times 900. I just went ahead and squared the 30. How much simplifying can you do on that without having to use a calculator? What could you do to simplify that without picking up a calculator? You could divide both numerator and denominator by 100, and those zeros would be gone. And then you could divide the 4 into the 8 2 times. And what's left of the left-hand side? 2 over 9 pi. Now, if you're working for NASA, you want to leave it 2 over 9 pi. If you're working for McDonald's, you're probably not going to be doing this. But if you were, a decimal approximation would be good enough. What are the units on that answer? That's centimeters. Oh, if you say cube, then this would be volume, and this is not volume, it's radius, so it's what? Centimeters. Radius isn't square units, radius is linear. So the radius is changing at a rate of 2 over 9 pi centimeters per what? This time was given in minutes. All right, I wanted to get 16. I don't have time to get 16. So what I want you to do for the homework is 1 through 13. 1 through 13 odd. And be working on those additional 20 problems, because today's the last day you'll have somebody during after school hours here. Tomorrow, Mallory and I both leave at 2 or try to. You can come in early. I will be here. I'm going to come on down to this room at 7:15 tomorrow morning. If you can't get to Mallory this afternoon, then you be here 7:15 tomorrow morning. Yes, sir. Yes. Okay, more. I brought that with me. Looks like you've got a common denominator for those two, and you didn't have to, just because I said so. But before that, you had x over square. Oh, yeah, x over x squared plus 1. Ooh, that would take me a minute to magnifying glass.
Sorry.
It would have been a whole lot easier if you had brought the 2 out front.
Right.
I'm gonna.
Was that a piano?
1/2 natural log of x squared plus 1 minus 2 natural log.
Oh, yeah,
Yeah.
that would have been a lot easier.
It would have.
Right. And then you could do the.
Actually, you could split that apart. The 2 only applies to that factor, so you could write that minus natural log of x minus 2 natural log of 2x cubed minus 1. And then the calculus would have been so much easier, and you could have just left it like that.
Okay, I'll just go check with Mallory tonight.
Okay. All right, she's here till 4:30, and then I'll be here at 7:15. Yes, ma'am.
You told me to do number 14.
Oh, yes,
for the
yes.
third time.
Okay, because I just wanted to make
I think
sure
I
you
got
got
it
it.
this time.
Yes.
Okay.
On here, you didn't use the product rule.
Right. Right.
Okay.
I was a mess. I'm a mess.
Just honestly, I was a mess. Okay, you keep this. It looks great. I'm gonna put a check mark by, did it? But I wanted to make sure you understood why you had to use the product rule.
Yes, thank you.
All righty, see you.
Okay.
You too.
We're on a field trip, so
Which one is this?
this one's a career fair at Tech.
Nice. Okay, enjoy it.
Thank you.